Welcome back. All right, welcome back. There are still some few people who are grabbing coffee, but I want to be cognizant of people who are from remote and it's late night there. I'll start by giving you some good news for those who heard that Dietmar lost his bag yesterday. He actually retrieved it. He found it. So when he walks in with his backpack, be ready to clap and cheer him on. He's the happiest man I've seen, I have to say. And he'll tell you, he'll share the story with him, but it's a happy ending. Another happy ending because 7 years ago, it was Naim who had lost his wallet at Netflix, and he also found it. So there is something magical about VQEG. We find the things we lose. All right, we go back to Sam, the statistical analysis method, and we have Panagiotis Straganitis, who will give us his presentation. Panagiotis, are you there?
Yes. Yeah.
All right. So please start sharing, introduce yourself, and you got altogether half an hour.
Okay, just 1 minute, please. And right. Can you see my slides?
Yes, we can.
Okay, great. All right. So, hi everyone. My name is Panagiotis Straganitis, and I am an assistant professor at the Department of Electrical and Computer Engineering at Michigan State University. And the topic of this talk is basically learning and inferring statistical models from crowdsourced noisy labels. Now, I'm going to preface this by saying that this is a very shortened version of a 3-hour tutorial that my colleagues and I delivered recently in the 2025 ICASP conference. And my colleagues are Sahana Ibrahim from the University of Central Florida, Xiao Fu at Oregon State, and Georgios Giannakis at the University of Minnesota. So this will be kind of a 25-minute condensation of that 3-hour tutorial, right? So to begin with, crowdsourcing basically is a learning paradigm that combines information from unreliable sources. We seek to figure out the truth by asking multiple, let's say, people for which we don't know the reliability. And the success of crowdsourcing lies on the fact that it simultaneously tries to assess source reliability and find the true information at the same time. Now, these unreliable sources may be crowds of human annotators, as the name suggests, or they may be simple decision rules, simple machine learning models, or video quality metrics, right? Now, crowdsourcing has enabled us to go from large unlabeled to labeled datasets in machine learning. So, for instance, if you've ever come across the ImageNet dataset, then that is a prime example of the success of crowdsourcing. And in order to label these datasets, we don't need any expert supervision. It's relatively low cost and facilitated by various commercial services, such as Prolific, Data Annotation Tech, or Amazon Mechanical Turk, just to name a few. And more recently, it has been very successfully used to train AI models such as ChatGPT, basically not exactly train, fine-tune them all. Basically, this is what is known as large language model alignment. And besides machine learning, it has been used in medical image analysis, citizen science, if you have ever used the Galaxy Zoo website, and crowd sensing. If you have ever used the Waze app while you're driving, that is also a prime example of crowdsourcing. Now, in this talk, I want to show you what a flexible framework this is. And we're going to talk about two paradigms from learning from crowds and potentially how it can be used for video quality evaluation. So to make things a little bit more concise, suppose we have a set of videos that we want to evaluate whether they are of good quality or not, right? And we dispatch these videos to a crowd of annotators. Now, with annotators, this is an umbrella term that I'm using to also cover, simple machine learning algorithms or video quality metrics, right? And these annotators, the responses that they can give potentially are whether the quality of the video is acceptable or unacceptable, or they can give an ordinal ranking on the quality with, for example, they can give 1 out of 3 stars, so 1 out of 3 ordinal ranking, with 1 being the lowest quality score and 3 being the highest. Or alternatively, pairwise rankings, basically telling us that potentially this video is better than this one, and so on and so forth, right? Now, the focus here is how we can combine the opinions of different annotators. And now the challenges are that basically we don't have any ground truth labels, right? We don't have any ground truth opinions necessarily to guide us into figuring out this combination. Furthermore, the annotators, in the case of humans at least, can be unreliable and adversarial. They can give us spam annotations. And when dealing with humans, we also have sparsity of responses when we have human annotators. Nevertheless, crowdsourcing offers a sense of redundancy or diversity, right? Which is the key to discover the true, let's say, score of each video, right? Now, another example, for instance, if we consider the case of VMAF, right? These annotators can be, for example, for instance, the elementary video quality metrics, and we seek to find out how to combine them without having any true labels. Now, for the rest of this talk, the prime example will be classification. And I will explain why we use classification in a bit. But for the time being, suppose that we have a set of n data, n videos, right, whose features are captured in a vector x. And the corresponding label, the corresponding score, let's say, is in this yn. So if we have k classes, we have a score of 1 up to k. If we have acceptable or non-acceptable, we have a +1 or -1. Now, we also have M annotators that observe subsets of the data, and they give us their labels, right, their opinions, which in general are noisy, right? So with check here, we denote the noisy opinion of an annotator. So the opinion that annotator 1 gave to data point xn is denoted like this, basically yn superscript 1, y check n superscript 1. And in general, our goal is, given all these noisy labels, we want to combine them, we want to fuse them into a y hat that hopefully is close to the truth. Now, to do this, we need to figure out 2 things. We need to answer 2 intertwined questions, which is, the first one is, which annotators are reliable? And if we know which annotators are reliable, how we can combine their answers. And I said we're going to focus on classification here because in the case of acceptable or unacceptable videos, this is a case of binary classification. And as well, ordinal ranking can be cast as a classification problem. So moving on, at the first part, we're going to see the first paradigm into combining labels, of course, very briefly. And then we're going to move on to the second paradigm, which is called end-to-end learning. So in the first paradigm, suppose that we have our unlabeled data, our videos, right? Or video features. We dispatch them to a crowd and we get a set of crowd labels. Here, the different colors indicate different annotators. Now, our goal here is to learn a function G that will take the labels from the crowd, which are collected in this calligraphic set, and essentially denoise them, basically find the fused labels. And in many cases, this may be all we want to do, right? But oftentimes we want to take these estimated labels and the videos we have or the video features we have and give them to a machine learning model and get a machine learning model that we can deploy whenever we want. And again, this is the most general case of a crowd sourcing problem. So in this state, in this paradigm, our focus is on figuring out this denoising rule, because the machine learning part happens afterwards. We don't care how that happens. So in the simplest way to combine labels is the so-called majority voting rule. Basically, this means that for each data point xn, the answer y hat that we get is the one that most annotators agree on. So basically, this is the indicator function that takes the value 1 if what's inside the bracket holds and 0 otherwise. And basically, this is the democratic, let's say, solution to the problem. Nevertheless, this majority voting rule assumes that all annotators are the same, equally good, and also it requires them to be independent, to make independent decisions. So the question becomes here, how can we do better than that, right? And luckily, we can, for my research, right, we can do better. And the simplest way to extend this is, for example, weighted majority voting, where we assign a non-negative weight to each different annotator, and this non-negative weight essentially captures the reliability. So if I know that somebody, one annotator is better than another annotator, I'm going to put more weight into their opinions than others. Now, the question also becomes, though, how do we find these weights? And for this, in the next few slides, we're going to see one of the workhorse models and very briefly cover the algorithms that are used for this. So this workhorse model we're going to talk about is called the David and Skin model, and it's a fairly old model. It's from 1979. And the first assumption we have is that our data pairs, our data tuples of features and labels are drawn IID from some unknown distribution. Now, since we have a probabilistic model, the standard way, let's say, to find y hat, the fused label, is to find the maxima posteriori, the label that maximizes the posterior probability of the labels given the observed data. So the y checks are my observed data, and these y ends are the things I want to find. And now, if you believe me, using Bayes' rule, we can rewrite this like this product of two probability mass functions. Now, the other assumption of the David and Skin model is that given the ground truth label yn, annotator responses are independent. Basically, this means that this m-dimensional PMF can be factorized into m one-dimensional PMFs. And essentially, also this says that annotators make independent errors, right? And the other way that you can think about this is like a naive Bayes model, where we are observing annotator responses and the hidden variable is the true label that we want to find. So given this assumption and taking the logarithm of this rule, we get this very simple rule, which of course relies on us knowing these probabilities, right? The problem is that we don't know them. Nevertheless, if we did actually know these probabilities, this map rule has very good performance. Basically, the error rate of this map rule reduces exponentially the more annotators we have. So this is also intuitive. The more people we ask, the more annotators we ask, the more simple algorithms we seek to combine, the better our error rate will be, as long as we find these probabilities. So how do we find these probabilities, though? Essentially, we treat them as parameters in our model. So basically, if you allow me, I will collect all prior probabilities of labels into a k/1 vector, and the per annotator conditional probabilities, I collect them into a k/k matrix. So for one annotator, I have for each annotator, I have a k/k matrix. And these, we call them confusion matrices because essentially, if we look at this example here, the diagonals of this matrix basically tell us the probability of correct labeling. So the entry 1, 1 will tell us what is the probability that annotator M gave the answer 1 if the true label was 1. whereas the off-diagonal entries tell us the probability of making an error for this annotator. So in this example here, this entry tells us what is the probability that we will receive answer 2 when the true label is equal to 3. Of course, this means that an ideal annotator will have an identity confusion matrix, but that is rarely the case. And we can also define more parsimonious model by assuming special structure of these confusion matrices. But again, we have to figure out these model parameters only from these annotator responses. So how do we do that? Well, if we open a statistical signal processing textbook, the first thing that's gonna tell you is to find the maximum likelihood estimate of these model parameters. So these parameters, we basically, if we collect all of them in a vector psi, we want to maximize the likelihood or the log likelihood of the observed data, right? Nevertheless, typically this is not something that's easy to do. So instead, we opt to use the so-called expectation maximization algorithm, which instead of maximizing this directly, finds a lower bound and maximizes that. So at each iteration, the expectation maximization algorithm estimates a lower bound of this function. Essentially, it figures out, it estimates the labels that we are looking for, and then it also updates the unknown parameters. So these two steps happen iteratively. And of course, the good thing is that if we have a lot of annotators and a lot of data, and we properly initialize the expectation maximization algorithm, then we can recover the correct labels with high probability. Now, there are other methods as well for this. For instance, we can use method of moments based estimation. And as an example here, I'm going to show you how we can compute the pairwise statistics of annotator responses. So this joint probability between annotator M and M prime. And this is something that we can actually compute statistics for. Now, if I use the law of total probability on this, it turns out that it has this structure, which basically contains the information I'm looking for. So method of moments based methods seek to map the empirical estimates of these statistics to their theoretical estimates. And there have been many non-negative matrix factorization and tensor-based approaches available. And also these approaches can give us identifiability. So we can be sure that these parameters that we find are identifiable. And also they can give proper initialization to the expectation maximization algorithm. To convince you that these things work, let's see a small synthetic data test here, where in this figure, we have the classification error rate of different algorithms as we increase the number of annotators. Now, this yellow line is the majority voting rule. And we see that even though it's simple, it does experience a decrease in error as we increase the number of annotators. So if we have a lot of annotators, majority voting may be very good as well. Now, this purple line is the expectation maximization algorithm we mentioned earlier. And this blue line is a method of moments-based method. And this orange line is a so-called oracle classifier, basically that has all the information, all the parameters that we are seeking. So here we see that as we increase the number of annotators, we do have an exponential decrease in the error rate. And we are approaching the oracle classifier. To further drive this point, we also have some data sets, some real data sets where the labels are collected from Amazon's Mechanical Turk. And here, the gist of these images, again, we see classification error for different data sets, but the bars here indicate different algorithms. Nevertheless, the gist is that methods that are extensions of what I briefly presented that guarantee identifiability tend to work better than ones that do not guarantee identifiability. So these three tend to work better across most datasets. Now, this idea of the expectation maximization algorithm, where I fix labels, estimate parameters, and then re-estimate my labels, and then estimate my parameters again, can be generalized. But what I want to briefly say here is that the David and Skin model is one of the core models for label aggregation. Of course, there are other models that capture instant difficulty, but we can also extend this to capture data dependency. Now, I know I went through this very briefly, but again, this is a much shorter version of the tutorial. So next, let's talk about end-to-end learning with crowdsourced labels. So here, instead of having a specific data denoising step that we had earlier, that we wanted to denoise labels, what we're going to do is we're going to take the unlabeled data and the crowd labels and try to simultaneously denoise the labels and learn a classifier. So essentially our goal, this is why it's called end-to-end learning, is to learn a function f parameterized by theta that corresponds to the optimal classifier. And again, there are two ways to approach this. The first one is, again, via expectation maximization. So we can consider the same model we had before. Again, we have the observed annotator labels and the data, but now we also have this part here, right? So expectation maximization still works in this case. So again, per iteration, we estimate a lower bound of the likelihood, which means that we estimate these labels here, we get an estimate of these, and then we update the parameters, basically the probabilities that define these annotator labels, and we also update our classifier. And this works very well, and there have been many classifier variants in this case, such as logistic regression, neural networks, and Gaussian processes. And this will work fast if your classifier can be updated fast, or in cases where it's non-differentiable, right? Nevertheless, the caveat of this method is that it requires the independence between annotators, and if you have, let's say, a big neural network that you need to retrain at each step, this may be a bottleneck. So more recent approaches opt for something that's called the crowd layer, and this is typically for differentiable models. So for instance, you have a neural network here, and you can consider the annotator labels connected to the data features through what is known as a crowd layer. Basically, these are, again, the confusion matrices that are multiplied with the output of this neural network. And the good thing here is that this thing is trainable via backpropagation, and you don't need necessarily to have conditional independence. Although most theoretical results assume some sort of conditional independence. This is a very flexible framework. You can put whatever you want as a classifier here. And in both the expectation maximization case and in this case, after you have done the training, you don't need any crowdsourced labels in the testing phase. And there are also methods that where the performance of each annotator depends also on the data feature. So some final results here, basically showing the performance of end-to-end learning. So these three colors indicate end-to-end learning approaches, whereas these two colors indicate two-stage approaches, where we do denoising and then we train a machine learning model. And in general, end-to-end methods outperform two-stage approaches because they actually take advantage of the data features. With that, I'll arrive to my conclusions. So the first thing, if you want to remember a few things from this talk, the first thing is that crowdsourcing can learn from unreliable information sources, and it can assess the reliability under certain conditions, of course. And the two major paradigms are the two-stage and end-to-end learning paradigms. Two-stage approaches require only annotator labels, and the workhorse algorithm over there is expectation maximization, but we also have moment-based methods. And end-to-end approaches basically use data features as well to learn a model and annotator parameters at the same time. And typically, because they use data features, they have improved performance. Now, of course, we didn't cover a lot of stuff. For example, what happens when you do regression clustering? How can you do metric learning? How do you learn a metric from crowdsourced annotation or ranking specific methods? Also, the methods that we mentioned can be adapted to identify spammer annotators or adversaries or annotator dependencies. And also there are active learning methods that collect annotations on the fly. With that, I'd like to mention that if you're more interested in this topic, the slides from the ICAST 2025 tutorial are in this URL. And also we have submitted, and we just got accepted for a feature article at the Signal Processing magazine, which basically covers what I said. It's called Learning from Crowdsourced Noisy Labels, a Signal Processing Perspective. And with that, I'd like to thank you all for your attention.
Thanks, Panagiotis. Before opening the floor for questions, I really want to allow me to say the connection that I saw, because I was in the audience of this. And I have to say that, in my opinion, there is a very obvious way to take the learnings and see how we apply it. We have traditionally, and just before the lunch break, we talked about conducting subjective experiments, aggregating results, and then perhaps training a model, right? Mm-hmm. That's the usual way. The first paradigm is what I think this community has learned to do over the past 30 years. And I think one of the key things that, at least to me, was eye-opening, we don't necessarily need to aggregate, right? We can actually feed through these matrices, the confusion matrices, while you are building. So I'm going back now 10 years. At Netflix, we built VMAF in the traditional way, right? And we said, okay, let's aggregate the data and then train it. But this, at least there is enough evidence that it's worth looking as an alternative, especially when we are actually doing this, right? All of our objective metrics are built based on a baseline. Yes, it is on the extension part of Panagiotis' talk, right? It's the regression rather than a classification. Even though we could actually change and make sure that our objective metrics were on a discrete scale, 1, 2, 3, 4, 5. And then it is a classification problem, right? I just want to give this connection to the group. And now I'm opening the floor for questions.
Thank you.
Well, I see speechless people, which is very rare in this group.
It was fast. I had to condense 3 hours into 25 minutes, so it wasn't.
Patrick.
Go first, please. Okay. Okay, thank you very much. No, it was not that fast. No worry. Okay. The thing is that in the field of video image quality assessment, as opposed to labeling, let's say, stuff for computer vision related task, we don't have necessarily ground truth here. So reliability of raters is one thing. Outlier opinions is a different thing. So as far as I have understood the talk, it's mostly about when you have a kind of ground truth. And here we cannot really say we have a ground truth for this when we are talking about image and video and opinion score. So how would you apply all these things in the case of opinion score? So you see, we should make the difference between reliability of an annotator and the behavior of an annotator in terms of its opinion, his or her opinion, which sometimes you can classify as an outlier, but maybe this is something absolutely valid because this is his or her opinion. So how do you see that?
So that is a great question. So in general, as you are correct that so far what I talked about assumes that there is one ground truth, but that is not necessarily the case, right? If you have multiple ground truths, there are extensions of these ideas that go into multitask learning setups. Of course, they are not as much explored because, again, because you don't have one single ground truth, it's not as easy to evaluate in many cases. But this is something I'm very interested in exploring, actually. So I would be more than happy to look into it.
Okay, maybe to expand this, I think in this group we did quite a lot of within VQEG, quite a lot of method to either clean up the data or identify specific behavior. So it could be nice actually to reach out actually.
Yeah. So again, let me just say that in my simple mind, the modification we did with Surreal and P910 is actually expectation maximization, right? So from that point of view, I'm happy that we at least I can say we're more or less aligned on the first way of aggregating data, right? But again,
if you restrict the work on crowdsourcing of these two items within VQEG, but this I think we did more.
More.
Okay.
Agree.
Okay, so
maybe one more question, and I know we have one more presentation. We're just a little bit behind.
Yeah, very quick. I mean, one of the things that interested me most is that you said in the beginning, the input could be also not just stuff that comes from crowd, but features. I mean, we have plenty of metrics. I think that compute features and then try to aggregate and maybe just taking out the features and then try to come up with something out of these features with this method could be interesting. I mean, just a remark. I'm not sure how much it is feasible or not.
Thank you. And I see Abhijay, maybe.
I just wanted to add one small thing, which is that in this system, there's this small issue where, let's say if the annotators are trying to, let's say the annotators are not paying a lot of focus while they are annotating. And in this like online sort of trying to learn from noisy labels, this can be a problem because it's very hard to predict or find those outlier annotators at the same time. And that becomes another moving part for this problem. So I think something else will have to be added on to this so as to figure out how they can be, how those people can be, the annotations from those people can be reduced.
So I'll let Panayotis comment, but my understanding is that as long as you look at the confusion matrix, right, and you put, for example, exactly the same number, then you have the random number generator is simulated by that confusion matrix. If you have the adversarial guy who like reverses all the answers, you put 0 on the diagonal. So in other words, the framework of having a confusion matrix is generic enough, in my opinion, that covers line clickers, right, where they always click 1, random number generators, spammers, and confusion makers. So am I correct, Panayoti, in saying that the confusion matrix covers all these spammers and all these unreliable annotators?
Yes, exactly. Essentially, the fact that we are using a probabilistic model, right, allows us to, everything that doesn't fit in it necessarily can be considered an outlier and can be, potentially removed. So indeed, if you have spammers, the confusion matrix becomes rank 1, and then it's relatively easy to detect them in that case. But again, that assumes that things like conditional independence hold, right? So
not coordinated. Yeah. So, all right. Let's again wrap up. I think we're a little bit behind schedule. Thanks, Panayoti, one more time.
Thank you very much.
And now we move to the next sum, which I believe is Mohsen. Am I correct? I hope so. But I don't see. who is not online. Okay. Seems like we're going to be rescheduling. Can somebody help me reschedule?
We're no longer behind. No, we're ahead.
Or maybe we'll just shuffle with the next presentation. Okay, we're gonna then move. So it is motion normally, right? Am I correct? Okay, please do. And if he's available, fine. Otherwise, we'll reschedule some other. But while we're waiting for Moxon to confirm what's the first, I'll pass then the microphone to Abhijay to chair the next Sogai session while waiting to see if maybe Moxon can wake up and dial back and give us a presentation. I know it's fairly late. Moxon, yeah. And maybe use the opportunity to speak about the group, yourself, the other co-chairs, because I did not give a proper introduction on Monday. So, do you have slides to show?
No, actually.
Okay.
Hi, my name is Abhijay. I work at Sony Interactive Entertainment. Sorry. So I work at Sony Interactive Entertainment. I recently started there as a ML researcher, and I'm about to complete my PhD from Portland State University. My PhD thesis is mainly on how to make perceptual similarity metrics more robust. And then I explore different ways where we can make it shift tolerant, we can add adversarial noise and try to figure out if those metrics can be more robust too. That sort of noise, perturbation noise on the images. And the initiative that I'm leading at Sogai is along with Lucas and Rakesh, is kind of very different from my PhD thesis. So we are focusing on generative AI artifacts, which are something which is like new and upcoming. And I wish I had a slide from our previous talk at VQEG where we showed these images generated by text-to-image models where there's a person's body, but the head is facing backwards, which is very hard to detect and like make a model to reason for that. Then things like common things that are happening with these image generations are that the number of fingers are not like it would miss out on how many number of fingers that are there in the generated. So I wish I had that slide to present. I'll try to find that and show that next time. Not next time, but in like a couple of minutes, if it's possible. So yeah, so basically, when we started looking into this problem, we realized that even with the latest models that have come up, for example, Flux, which are generating very high quality images, it is still leading to some or the other failure in their generations. And it's if you go through like hundreds of images like we did, we could pick out like 1 out of 100 image, 1 out of like 100 images where things were, there was something off in the image. I think that's something which would be very interesting to look into from the VQEG community, where we can all come and work across institutional boundaries to figure out a way in which we can evaluate these images, which is very hard. And I sort of wanted to try how the different Gemini and GPT-4o and 4.1 models do on this particular task. And I think they're going to do really well. So I just wanted to try that out and show it to you guys this afternoon. But yeah, it's a pretty interesting new and upcoming field. And I would like to thank Yanis and Margaret and members and chairs of the NORM community who helped us form this group, and hopefully we would like to see more. Hopefully, we see like more participation from everyone, where we're able to collect some data and run some subjective studies. So that's one of the things that we want to do. Yep.
Thanks again. We're going to go a little bit back and forth. Is Mohsen ready? I see him online. Yeah. Okay.
Hi.
So hold that thought. You heard the introduction about Sogai. There will be the actual presentations coming up, but let's go back to our order. Mohsen, are you ready to give us the final SAM presentation? All right.
Yes.
Go ahead.
Hello, everyone. Do you see my slide? You see the slide?
Yes, the answer is yes.
Okay. Thank you very much. Hello, everyone. My name is Mohsen Janadile, postdoc researcher at the University of Constance, Germany, and I will present our work titled Subjective Visual Equality Assessment for High-Fidelity Learning-Based Image Compression. Deep learning-based image compression methods such as JPEG AI have shown improved rate distortion performance and perceptual equality compared to traditional codecs. JPEG AI leverage neural network for high quality image reconstruction. However, this new compression method introduced novel artifacts. These artifacts are not fully captured by traditional image quality metric like PSNR or SSIM. Highlighting the need for rigorous subjective image quality assessment. Our objective in this study were to extend JPEG AIC3 image quality dataset by including JPEG AI compressed image alongside with the existing image set, which included image compressed by JPEG-1, JPEG 2000, AVIF, JPEG XL, and VVC. Also to evaluate perceptual quality of JPEG AI image using the JPEG AI C3 methodology through large-scale crowdsourcing experiment. Also to benchmark several objective image quality metric and compare their performance. These are the source image we used in our study. These sources are from JPEG AIC3 dataset representing diverse visual content. We use the crop of 620 by 800 pixel from the full resolution image were carefully selected by the group to preserve key visual detail for our subjective testing. Each source image was compressed using JPEG AI at 10 bitrate, ranging from 0.3 to 1.625 bit per pixel with a step of 0.15. We visually check that this bitrate more or less the distortion would match the distortion of the image in the other codecs. We use JPEG AI VM 7.0 with this command to generate this 10 compressed version per each source image. In total, we generated 50 compressed image for JPEG AI for 5 sources. So our objective evaluation followed the JPEG AIC3 protocol using two triplet methodology, plain triplet comparison and boosted triplet comparison, which the boosted will amplify the visibility of the distortion through zooming, artifact amplification by factor of 2 and flicker effect. BTC evaluation include all the 10 bitrate, so we created all the same codec triplet with for all including all the 10 bitrate, and for the PTC only 5 bitrate were selected, level 2, 4, 6, 8, and 10. So the BTC involves 660 triplet divided to 5 batch of 132 question each, and the PTC consists of 180 triplets split to 2 batch of 90 question each. Then we run using the web interface of JPEG AIC3. We run large-scale crowdsourcing, and we collected 49 responses per triplet for the PTC and 120 responses per triplet for the BTC. Overall, 96,200 triplet comparisons were collected from 459 participants, 73 crowd worker for the PTC and 386 for the BTC. We perform the batch level screening based on JPEG IC3 methodology. So it is calculate the accuracy if the user select the in the same codec comparison. If the user select the image with the lower quality as with the lower bitrate as the lower quality, then his decision is correct. And the consistency assessing through the agreement in the response to the mirror question pair. Dietmar detailed this in his talk. I don't want to detail more this. And then we use combined accuracy and consistency threshold based on the Otso threshold is decided, and we filtered the batch with the lower quality. So for the PTC, 51 from 98 were filtered, and for the BTC, only 46 from 600 batch were filtered. So again, we use the JPEG AIC reconstruction method to reconstruct perceptual quality scale in a fractional GND unit. Exponential rate distortion function was estimated using the unified model Dietmar detailed in his talk number 118 proposed by JPEG AIC3 and which uses apply maximum likelihood estimation jointly to the BTC and BTC responses. This result, as you can see in this curve, the red curve are for the JPEG AI and the gray for the other codecs. And we showed this with 95 confidence interval through bootstrapping. As you can see that JPEG AI perform very well and provide very good quality in lower bitrate. So we evaluated several objective metric as well, and in here that overall, when you see there, it is for the all image from the all 6 codec, not only JPEG AI, and for all the image for the 6 codec, CVB DP perform very well, and it has the highest performance for the overall and per source. However, for JPEG AI, VMAP NEG performed the highest performance, and CBBDP could not capture the distortion that caused by the learning-based compression. And here you can see we also plotted the GND versus the quality scored and fitted a logistic function for visualization. As you can see, almost all of the metric, they overestimate and optimistic about the JPEG AI compressed image. And to compare the performance of the correlation of the metric, we use the MRR test to compare pair of the metric based on their Spearman rank order correlation coefficient with the subjective GND score. The MR test assesses the statistical significance of difference in the correlation value by considering the correlation between 2 metric and their shared correlation with the subjective score as a dependent variable. It computes test statistic based on the Fisher transform of correlation and account for metric interdependency. So based on that, you can see the result here that this is only for the overall, for the all 6 codec. the CVVDP performed the best between this compared metric and also IWSSIM. So in conclusion, 15 for reference image were evaluated. Most metric overestimate the quality for JPEG AI, as you saw in that graph, and best performing metric it was CVVDP for the whole for the all 6 codec, and VMAF-NIC for the JPEG AI. JPEG AI deliver good perceptual quality as low bitrate, so it was very promising, and subjective testing remain essential in high fidelity image, especially for this new kind of distortion, and the statistical evaluation also, it would be good to perform to compare this performance if they are really statistically different. All the source image, the triplet responses, the GND reconstruction, and the script for this result are available online. Thank you very much.
Thanks. Thank you, Mohsen.
Thank you.
Opening up for questions, I see Lucas.
Thank you. Thank you, Mohsen, for the presentation. A quick question. Could you come back to the table with the correlation results for the metrics?
Yes.
Yeah, one thing that confuses me, and let's just focus on the JPEG AI now, is the difference between performance of VMAF and VMAF NEG. Because VMAF NEG is supposed to suppress the sensitivity of VMAF to cases where the codec, for example, increases contrast or introduces changes that are supposed to post-process the image. And normally, I would expect that if that would be happening, could you comment on how do you explain, or what is your view on the difference of these two metrics and what is causing the better performance? Also considering that your subjective protocol did not have any, or it had a reference there, right? Yeah. Okay, so that's that should be capturing already the difference between the reference. And okay, maybe I'm answering my own question, because if there was some sort of improvement towards the reference, people would hate it, right? So that's explaining it. Okay,
yeah,
well,
discuss this also with Jonas.
Thank you so much for guiding me through this.
we discussed this with Jonas Nair as well when we reported this. It was also surprising for us in the first class. And we discussed the similar issues could be the reason for that, but it's hard to, we didn't come also to really to fully understand why the VMAF negative it can perform such much better than VMAF.
And by the way, it's called the Socratic method, but you need 2 people in the Socratic method. Now you are both Socrates and Lucas at the same time. So you answered your own question, Q&A, very impressive. No, but allow me to put my thoughts on this one. Let's start by remember what VMAF-NEG does, right? Which Lucas started saying. For cases where, let me use the word quote unquote, things look better, and VMAF would report, I don't know, 105, because, for example, contrast stretching or histogram equalization, VMAF-NEG would capture that and take the areas of the image where this is happening and lower the performance. So in general, VMAF-NEG is a lower number. Just remember that rule of thumb. You run VMAF, you run VMAF-NEG. I see very few cases where VMAF-NEG can be higher than VMAF. I think mathematically impossible, which means to me that if you draw those lines that we saw where you said it overestimates the quality, VMAF overestimated the quality, and that's why it was further off. Would be my Socratic back and forth on my explanation. So VMAF-NEG lowers the numbers and puts them closer to the ground truth. But that's just a theory.
I mean, it is not only for JPEG AI, it is for the other codec also. VMAF-NEG performed better than VMAF.
even though within the statistical error. Yes, you're right, but still the gap is very pronounced for JPEG AI, right?
Yeah.
Okay, any more questions for Moxon? Okay, hearing none, thank you.
Dietmar can comment one thing that in JPEG AIC3, there is call for proposal for the objective metric. Dietmar, you want to comment on that? Maybe to re-announce it?
Yes, okay, so here we have many metrics there applied to the whole data set. They were fitted with the logistic transformation to give the best performance in PLCC. And these, or some of these now function as anchors for the JPEG AIC4 call for proposals. And so the objective for proposals would be to, to get metrics that would beat these anchors. Okay.
Yeah, so Dietmar, I mean, you can announce it to invite people to submit proposal for that.
Yeah, sorry, this actually gave me one more thought, and I hope this is going to be actually a question.
Yeah, sure.
Since you had the triplets, those were mostly only within content, right? Within one source.
Yes.
But then we are merging all these things together in a scores. Could you comment on how reliable the scores from one content to another are when we are comparing cross source?
You can see them here for, I mean, we're in here. You can see each of these curve is for one source and for different codec. In the gray, you don't see which codec it is, but the red one is for the JPEG AI. They are more or less, they are aligned to each other. It's not very, so you have almost distortion level between 0 to 2.5 GND for 10 different distortion level. For different sources and for different codec. Maybe source 9 a bit off for JPEG AI, but not the other.
Yeah, I'd be mostly, curious on how, because you do see that there's a drop, and I'm just wondering if that drop comes really from the worst performance across the content, or if it is also coming from the fact that maybe sometimes we are forcing the metric to make a choice that we are not certain about from the data, because those cases were not really present there. So that's mostly just my nitpicky question that I don't really have too much view into.
You mean in the efforts in the subjective evaluation, or in the estimation
so
of the GND?
we are very certain about the data within the source, because those are basically already present there. But
Yes.
when you get a score of, let's say, JND something on one source and on the other one, are they very much comparable to each other?
You can see them here. Yeah, this is for different sources, the GND for 10 different distortion levels. They more or less, they are on the same scale, except for source 9 a bit. For JPEG AI, it's a bit different. But more or less, I mean, JPEG AI in general have a bit perform better in the lower bitrate, will have a higher quality. But the range of the range of the GND is almost more or less the same between 0 to 3, or for this in the distortion level. Yeah.
Okay, got it. Thank you.
Okay, so unless there are any more questions, let's thank the speaker one more time.
Okay, thank you very much.
And we can move in anticipation. It was supposed to be after the break, but let's use the time and maybe buffer some time in the end, either for discussion or people, go earlier to take a break before the dinner. So I'll pass the microphone again to Abhijay, who will show us a few slides, and then we'll go through the presentation.
Okay, so this is what I was talking about earlier. So I just took these images from our slide in the last VQEG, and I just ran Gemini 3's, sorry, not, I think it was Gemini, let me check. Yeah, this was like the 2.0 Flash model, which is still simpler than the more recent reasoning models, which are slightly more advanced. And I'll give you guys a moment to look at these images and try and figure out if you see any anomalies or any issues with these images. So the most obvious one is the bottom left corner, where there's a boy standing and he's basically facing in the front, but the head is turned completely backwards. So that is an easy one. And now if we start looking at what reasoning or just like what the Gemini 2.0 Flash model predicts. In the first one, it says correctly that the text on the can appears nonsensical. It doesn't seem to be from anywhere. It seems like random gibberish. Then in the middle is again shattered glass. It seems like an art piece, but there's some text or quote from. But then again, that text also does not make any sense. Third one is the dog, my favorite, which is like a dog it's reading. It seems improbable that a dog would be reading, but then it's like a cute picture. The issue I see in this image is with the hands of the dog. It looks very unnatural. It seems like the hand is split and the leg is coming out. I shouldn't say hand. Dogs have legs. Sorry. This one, it again predicts correctly, where it says that the over here it just is not able to figure out what the anomaly is in the image. Then in the middle is these are very weird hands. This is like a very common anomaly in text-to-image models where they're not able to create proper hands. And lastly, these bell peppers. I've never seen such bell peppers. They're kind of like very round and look they look unnatural. So I wouldn't say that this is like a image which would be found on the internet. It definitely looks generated. So as a user of a model of a text-to-image generator, I would not be happy with this result. But then again here, the reasoning which the model gives is kind of weird. Like it's incorrect. It's focusing on something else than what I think. So so these are the kind of things that we can do at SOGAI, and a lot more. I think some of the talks will talk about that. So the next coming talk, the upcoming talk is by Ryan, and I would give him the mic to continue, and we can look into more interesting things. Thank you.
Why don't you set up? So again, just I'm taking the opportunity to ask a poll question. We are scheduled for 7 p.m. dinner, but there may be opportunity to anticipate like 6:30. Is there a preference in the group? I thought 7 would give enough time. People go back to hotel, like take a short rest, not just rush from here to the restaurant. Shall we stick with 7? 7. Last, okay, 7 will be. And then because we are ahead of schedule, I'm not going to be pushing anybody either for the break or for the talk. So let's a little bit relax. But then we said that you have like 20, 25 minutes, but I think you have more time if necessary. I'll give you this. Check if that one works. Open.
Hello, hello. Yeah, it works. Okay, cool. Hey, hello everyone. My name is Ryan Lei. I'm currently working at Video Infra at Meta. So our team is mainly responsible for all the backend processing of all the videos we got uploaded from many family of apps, including Facebook Reels, Facebook and Instagram. So today I want to take this opportunity to, together with my colleague Qi, want to share some of learnings we had from a recent study that leverages the subject evaluation for super resolution. Before I get started, basically I will cover the context and the motivation for this study and explain some challenges we are facing when trying to deploy super resolution at scale. And then I'll talk about how we prepare the test data set and for the subject evaluation. And then Qi will carry it over to share with you more details about the methodology we're using and the source, some of the preliminary result, and eventually we'll share some of the high-level learnings and some call for actions. So basically, this diagram is kind of a very simplified view of our end-to-end production pipeline. So at the ingest side, we can receive all videos uploaded from different sources through different apps. So it could come from just user capture video and they upload it to our platform, or it could come from some other platform, like some user download from YouTube or TikTok and then they re-upload to our platform. Or it could come from some editing apps, or could come from more kind of the recent AI-generated videos. And then some of the videos will have lower resolution and lower quality. Then when those videos come to our data center, we have option to apply some enhancement to improve this quality. Then super resolution is one of them. So after we apply super resolution, then we create a new kind of enhanced source. Then we use this enhanced source to go through conventional ABR encoding to produce multiple encoding lanes with different codec resolution and bitrate, and those will be used for delivery and consumption on the client side. So on the client side, based on your network bandwidth, the player will get the different resolution and different bitrate video for playback. And at that time, we also have option to apply super resolution. If the client eventually get a lower resolution video, then we can apply super resolution to enhance it. So obviously for super resolution solution on the client side, because the compute capacity, then we have to use some simpler algorithms. Well, but on the server side, we have room to accommodate more complicated and advanced super resolution algorithms or models. But for our end-to-end production, we do need to have very kind of sophisticated quality metrics and loggings for checking the quality improvement or degradation at each stage. So then when we deploy different technology at scale, then we can know at each stage what are the quality impact from different modules. So this is a kind of very important requirement for us to launch and roll out any new features. So specifically for super resolution, when we're trying to deploy it in production at scale, there are some challenges we are facing right now. So first is right now we don't have a very reliable quality metrics to measure quantitatively how much quality improvement we can get from super resolution. At the same time, from our observation, we also see like if the input quality is already very bad, then when you apply super resolution, sometimes it can amplify the artifacts in the original video, make it look even worse. So in that case, we don't have a way to accurately detect artifacts or issues can be introduced by super resolution. So to solve those challenges, we're trying to leverage subjective evaluation to see, trying to help us to answer some of the questions. First is, can we leverage subject evaluation to understand the quality improvement from super resolution? Based on this, how do we know which super resolution algorithm performs better? And also, can we leverage subject evaluation to understand how do we identify artifacts that could be introduced by the models or algorithms, and how do we identify, detect those edge cases? And the third question is also we're trying to answer, because when we're trying to deploy that skill, we cannot watch every video, then we have to rely on some objective metrics. Now, which objective metrics correlate with subject ratings, right? Then how do we kind of deploy those metrics along with the super resolution technologies? And also, how do we, for some videos, we know if it's very simple, then you probably, when you apply super resolution, you probably won't see any material gain. So how do we predict for different content, are we gonna get quality gains from super resolution or not? Okay, so all these questions, it can be applied to other general enhancement features as well. Here I want to share some details about how do we prepare the test data set for this study. So we're leveraging the public YouTube data set specifically for short form video. So in this particular data set, there's about 2,000 1080p videos. All of them are vertical with different content categories, and which is very close to the production video we are receiving. So from this 2,000 videos, we kind of select a small subset, about 50 videos with different content categories. From this set of video, we first downscale them by 2 with Landsat 5, and then we encode the downscaled video with X264 different CRF values to simulate different compression level and different quality we received from our client. Now, with this downscaled lower resolution video, we apply different upscaling or super resolution algorithms to produce the upscaled version. And then we also, in order to avoid any quality degradation, we also encode the upscaled video with very lower CRF value to make sure we don't introduce actual artifacts from the encoder itself. And then this upscaled version, because we have the original high resolution video, then we can calculate some quality metrics, either reference-based or non-reference-based, to compare the quality difference between the original high resolution video versus the processed high resolution video. In this study, we include few kind of super resolution algorithms from the most simplest, like bicubic line source, which are mainly used as a baseline because this is what most of the display engine will use for upscaling video. And also we include few ML-based super resolution models like Razor, EDSR, and also GAN-based like models like Real ESR GAN. In our production use cases, we mainly focus on 2x upscaling because most of the videos we deliver to the mobile platform are still 720p and 1080p resolutions. So we focus on 2x upscaling instead of like 4x or 4K resolutions. This diagram shows the objective metrics we calculated just from the test data. The x-axis is the encoded file size, which represents the bitrate after the upscaling and encoding. The y-axis is the VMAP score. So from this chart, you can see that we can roughly get an idea from VMAP score. Looks like this particular algorithm, this is EDSR, shows better quality. comparable with real ESR gain. But at the same time, we do see like different algorithms tends to introduce different high frequency signals, which cause the file size increase, which in this case you can see for Razor, probably you can see that the file size is the largest among all different algorithms. Yeah, so this is the data we can capture before we actually do the subjective evaluation. So now I'm going to hand it over to Qi to talk about the actual subjective evaluation methodology and some of the results.
Thanks, Ryan. Now let me talk about how we do the subject evaluation. So the protocol is like we present a pair of videos side by side. And meanwhile, we ask the crowdsourced annotators to answer some questions. The first question is about labeling the Mohs score in the very classic 1 to 5 scale. Thank you. On top of that, we also ask the annotators to check box what kind of artifacts they have seen during this video playback. And here is how we assign this annotation task. So we have a data set called the evaluation data set, and item 1, 2, 3 is mostly like video 1, 2, 3. And models here is a general term. It could be just a different super resolution algorithms. Model A could be EDSR, model B could be real SR again. So those are different algorithms. What we do is that for each source video, let's say item 1, we generate the enhanced videos using 2 versions of algorithms. For example, model A is EDSR and model B is bicubic. And we assign this pair of generated videos to an annotator for them to do a pair comparison. And during this pair comparison, as we mentioned, they will answer some questions like the Mohs score, ACR based. And as we know that the human labeling can be very noisy because of humans' bias, because of the human's inconsistency or the ambiguity of the content, we need extra processing to remove that noise. And the method we used is the serial analysis. And at high level, we aggregate the results at video level and looking at all the annotators across that video so that we can calibrate the annotation and get the serial recovered version. And we also want to get a score at a dataset level. And here we use the bootstrap resampling version of the analysis to get a mean and confidence interval at the dataset level. And we know that as we are doing the subject evaluation, in the product team, we want to move fast. And what matters is how fast we can finish one round of evaluation and at what kind of cost in terms of money. And in order to achieve the most cost-efficient way, we analyze how the confidence interval is impacted by this number of videos and number of annotators. And we want to make statistic decisions because those have product impacts. And here is the analysis in this table. Here we did a pilot test, and at the level of 40 videos and 10 annotators, and all the other data points are based on the extrapolated by this pilot test, so that we can know if we use different number of videos and annotators, what will be the confidence interval, and choose the trade-off that so that we can make a statistic decision, but still at the most cost-efficient way. So we just talk about how we did the subject evaluation, and now it's about how we want to do the objective evaluation, because our ultimate goal is to can we evaluate the quality at scale and using a more cost-efficient way. And objective evaluation is exactly more ideal than this subjective evaluation. And the metric we explored is this UVQ metric. And at high level, the UVQ metric extracts three kind of distortion signals, like the content type, distortion type, and the compression level, aggregating all the information and predicting a quality score in the same scale as MOS 1 to 5. And we verify this UVQ and see how well it is aligned with our subjective ratings. So here is the first kind of analysis we did. So in this chart, we actually did is a paired t-test. And here the baseline we used is the bicubic algorithm. And for each bar, it is related to a different super resolution algorithm. For example, this bar is related to real SR again. This is related to EDSR again. The x-axis is about the level of improvement compared with the baseline. That means the higher, the better. Like in this chart, the real SR again has the best improvement against the baseline. And also the color matters. The color with a green color, it means there's a static improvement, while gray is not static. So that, and this chart is based on the real MOS score. And in parallel with this MOS, we also calculated the UVQ score. And we measured the delta between this baseline algorithm and the super resolution, more advanced super resolution quality score, and calculated the delta. So that in this chart is about a delta UVQ score. For each column is related to a different algorithm. And in the y-axis is also about the absolute improvement of this predicted by UVQ. And here we can see real SR again is the best improve the baseline, following by the EDSR again. So the ranking order of these preferences that aligns well with that of the subjective evaluation. So this is based on our internal data set. And also we benchmark this UVQ in external data set like VQC and get also a reasonably good correlation like 0.6. So that is the first level of checking how well it aligns with subjective evaluation. And we also know that the objective score UVQ can do better than that. It can help predict how well this super resolution algorithm can actually improve the video quality even before you apply this algorithm. So here is what how we did the analysis. So our insight is that for videos with the quality is already bad, like there's already artifacts, blocky artifacts, blurry, like unnatural objects. If you do the super resolution, those artifacts will be amplified, and it's not ideal in such cases to apply super resolution. And hopefully we can have a metric to measure this source quality, and we don't want to apply this super resolution below that threshold, quality threshold. And we use UVQ and experimented some thresholds, and we found that if we slice the human evaluation results by UVQ 2.5, we found some interesting results. So in this chart, all the videos are UVQ quality below 2.5. In the right chart is for the videos above 2.5. And we see that for those videos with bad quality, there's actually no statistic results after applying the super resolution that aligns with our hypothesis. Well, for higher quality videos like above 2.5, we still see the significant quality improvement. So that aligns with our hypothesis that UVQ can actually predict whether the super resolution can make a difference. And this is important because at meta scale, applying shaping a super resolution algorithm is at a significant cost of the server capacity, storage capacity, or at client means the battery reliability. So we really want to do this in a cost-efficient way with high ROI. And using UVQ can help us make such kind of a wise decision. Right, you want to?
Yeah, so through our subject evaluation, we also noticed few interesting artifacts that could be introduced by super resolution. So we want to share some of the examples here. So one super resolution algorithm could introduce noticeable color differences as shown here. So left-hand side is an original image, and right-hand side is a processed image. There are also some super resolution algorithm, especially GAN-based. It could over-smooth, over-sharp the video image, make it more like a cartoonish. Right, so this is one example. Maybe you can not see it from the screen share, but if you focus on the face, you will see on the right-hand side, this is processed by a ML-based algorithm. The face region is more like cartoonish and animation. So this is another example. You can also notice, especially the face area, because when you look at the people from far distance, the face is supposed to be blurry at a similar level as your jerseys or other background. But if you enhance, make the face become more kind of sharper than the surrounding jerseys or other objects, it could be very easily to be observed and introduce a very kind of annoying, impressions. Yeah, so want to kind of summarize some high-level learnings first. As Qi mentioned, we identified a minimum quality threshold using UVQ. So with this threshold, we can kind of filter out all the bad quality videos before we apply super resolution. And we're also seeing like UVQ shows very strong correlation with human subject ratings for super resolution. We also noticed like when we have the high resolution ground truths, right, as I showed when we prepare the test data, we can actually see the reference-based metrics, the VMAP, also correlate quite well with UVQ and also the subject rating. So basically, this gave us some idea that if we have the ground truths, then we can actually also calculate VMAP to use it as a proxy to evaluate quality improvement from super resolution. And also, most importantly, we build this evaluation framework internally. We kind of make sure we can automate all the process flow and all the questionnaires. And this framework and the methodology we used, we see like from super resolution evaluation, it can capture very good signals for us to do post-analysis. And this framework itself can also be extended to other similar subjective evaluations for other enhancement features. It also has some limitations for the existing method. We have observed that the human reader have very different preference or tolerance for different artifacts, such as over smoothing, over sharp. So there's no metrics to, quantify if the video or image is over smooth, over sharp. Also from the study, because of the cost, we only introduced UVQ as objective metrics. We haven't got the chance to try some other metrics. So it could be some other metrics could be better than UVQ. And also, we know some super resolution algorithm was initially developed for image. And then some people just make it, trying to use it for video as well without considering the temporal consistency between frame. So initially when we designed this test and the questions, we're trying to ask if the rater can identify the temporal inconsistency issues from the subject evaluation. But unfortunately from this round of study, we don't have a very clear signals. So like the rater cannot detect the temporal inconsistency issues. But from some offline tests we did internally, we do see in some cases there's such issues. And also we feel like right now we're just using the cross-out raters to do this evaluation. We don't have a way to inform them to watch it in certain conditions or certain platform. And especially because most of our target devices are mobile devices, we don't have a standard way to conduct this type of subject evaluation on mobile platform. And another limitation is I mentioned we did not include the evaluation also consider the downstream ABR encodings. So given this is an opportunity for the VQEG meeting, so we want to take this chance to also hope like the group expert can help us to develop more reliable quality metrics, especially for other general ML-based pre-processing features as well. And also, if you are working on training such models or algorithms, I'm wondering if it's possible to also include certain quality metrics into the training process as a loss function to avoid such issues like the color difference, all those issues we mentioned in the previous example. I think that's all we have, and thank you for your attention, and we're open for the questions.
Thank you. We do have time for questions. Is there a third microphone somewhere? I see 1, 2, where's the third? That one is not working, unfortunately. This one battery died. So you need one. I'll steal from cell. So while Abhijay is preparing, I just want to refresh everybody, right? This is probably the most straightforward, quote unquote, Gen AI type of videos that are highly anchored into real videos, right? So you're only taking an exact video and you're making a few pixels, quote unquote, a little bit different, right? Different from the text to video that was discussed by Abhijay. But I would say it's the closest bridge or the closest gap to go from the traditional videos to this new era of generated videos. Is it on? Turn on. Another button.
I think I can just
double. No, no.
Okay.
The people on the Zoom can.
Right. Okay. So I think for the first point, where you're saying that there's no metric to quantify individual artifacts, I think there are some recent works on that. One of them is Clip IQA, where you can give antonym pairs and see. So for example, you can give a text like sharp image versus the other would be like blurry image or something like that. And then based on those antonym pairs, it'll give you some score. And it seems to work pretty well. And the other one is GPT-4V. I think you can just, although that's an expensive API, and also if you're using any of the large vision language models, they might be able to give you like the exact text description of what the artifact is. And I think that can be used for this particular task over here. So yeah, that's an interesting thing to try, I think.
Okay,
next.
yeah, thanks for the suggestion.
Thanks, Abhijit. Any other questions? I saw a few people raising hands. Patrick.
No question from Balu. Can you go back on the statement when you say, yes, we have identified the UVQ above 2.5. So I try to well understand. I think it's the next slide. Yeah. So the statement that you when the UVQ tells you it's above 2.5, it's where you can benefit from super resolution, and this is because you did this split and you don't see any improvement in terms of subjective quality assessment when UVQ is below 2.5, and you see an improvement when UVQ is above 2.5. Yeah, of course. Yeah. Okay, so it's a strong statement, and I'm not sure the conclusion is right. Because we know that UVQ is not well fitted above for score below 3 or 2. Okay, and there's good reason for that, and I think Balu can comment that eventually. But it's because it at me UVQ, as you mentioned, is a deep learning approach for video quality assessment, and it has been heavily trained on contents that are actually of quality of 3 or more. So that means below 3, you cannot really trust UVQ.
I see. Yeah, I think that's a good point.
And then just want to make sure we are on the same line with the conclusion. That means, okay, you certainly when you are, it makes sense when you have UVQ, anything you want to compute with UVQ above 3, you can certainly rely on that. And I think your data shows that in the case of super resolution, UVQ is pretty reliable to estimate improvement of quality, because this is what you get from the subjective score. But actually, UVQ is not a good proxy to decide anything else, anything below 3 or 2.5.
Just a question that this is a fact, right? So again, I forget how UVQ was trained for a moment. It's a black box for me. A video comes in, a number comes out.
Yeah.
Every time it was less than 0.5, and you applied any of these, a random number came out centered around 0. So there is nobody disagreeing that for this class of videos, maybe the UVQ was wrong. Maybe it was not 2.4, maybe it was 3, maybe it was 2.1. We don't know. I agree. But for the current version, what I read from this, anything that was 2.5 statistically did not improve the video. Can we agree on this statement?
No. Let me no. The thing is that you cannot use UVQ below 2.5 to demonstrate if you have an improvement or not an improvement of super resolution.
The pudding is here, right? This is the pudding. More score whenever UVQ was less than 2.5.
Yeah.
No improvement. Yes or no? Unless I'm misreading. Let's talk the grandfathers.
Yes, I think maybe there are some misunderstandings. So UVQ score below 3.0, it has a higher confidence interval, but all of them are low quality videos, that's for sure. And I think the motivation here is that since the source is already low quality, make it a super resolution will amplify the artifacts. So there is, it will make the quality worse. I think that's, yeah.
But I prefer this statement that when you say that a source content is of too low quality, there are poor chance that you can improve its quality through super resolution with the current super resolution algorithm that has been tested. And I prefer this conclusion than the one that we had on the slide. I think it's more accurate to put it like that.
Unfortunately, you're letting go into microphones, so either I run or people who want to speak up come closer, but please, let's keep the balloon.
Just a quick note, Patrick. I think as a general direction, UVQ identifies quality, and below 3, below 2.8, it gives you an understanding of which way to go, right? It gives you an estimate directionally. You're right, it doesn't, the correlation decreases as you go below that. Absolutely. However, for directionality, if you identify, it doesn't matter if it is 2.5, it is 2.8. What I think Ryan is looking for here is that, like, can we identify low quality videos and create a threshold where, like, if you amplify that, if you go from like 360 to 480 or 360 to 720, will the artifacts take over, or can I still have good quality? Where is that threshold? And I believe he's using UVQ to identify that threshold. And it really doesn't matter like where that threshold is. If the experiments were done at 2.8 and showed the same result, I would have believed it.
Yeah, exactly. So in production, we need a threshold to tell us whether we should apply super resolution or not, even though this threshold may be too conservative, or but it's rather than it's better than we kind of applied it to make it even worse. Right?
The way I see it, it's 12 of a kind or a dozen. It's the same thing how you call it, right? So it's low quality and you don't apply, or you don't apply because it's same quality, low quality. Is it really as low as it claims it is? Is it low? Or is it? Yes, it could be noisy. It could be that the 2.5 is actually 2.8 or a 2.1, much higher noise than if it estimates 3.2. There is no disagreement there. But the fact that whenever a threshold was put, there was no statistically observed improvement does not change.
Yeah, but once again, because it's kind of, we don't know if there's an improvement or not.
Oh, no. There was some where there was an improvement, some where there was a deterioration statistically.
If you look for left-hand side of some you have improvements, some you don't have. Region is so high, and
we don't disagree. We just say statistically means on average there was no improvement.
A question: the 3 videos you showed us with the artifacts, were these UVQ above 3 or below 3?
I think it's UVQ above 3. Yeah, for example, showed here. Sorry. Yeah, so this is a very high quality video. Yeah.
But this is a different type of artifact, right?
Right.
Chromatic aberration, if you like to call it, right? Oh, okay, Cosmin, and I see Lucas, and maybe then we go to coffee, continue the discussion.
Maybe I missed this part of it, but so coming up to Patrick's question about 2.5, I mean, at 2.5, we see this effect. What happens at 2.6, 2.7, 2.8? Did we find 2.5 as being like the most optimal threshold, or we just separate to look at 2.5 and says it works good enough and let's just leave it?
That's about it.
Yeah, so we also we observe with different super resolution algorithm that threshold could be different. For example, Razer, we might need the UVQ to be above 3.0 to see the improvement. But for real ESR, again, maybe the algorithm itself is better than we only need the UVQ 2.5. So we do say with different super resolution algorithm that threshold could be different.
No, that makes sense. But I mean, how specifically do you determine where the threshold is? Like,
I think we just did some offline slice and dicing. Yeah.
Okay, so could you go back to the, just a favor for me, go back to the original slide where you just showed VMAF and bitrate, because I think that's maybe people miss the point here. And I want to maybe lead to coffee because this may lead to a big discussion. To me, that says on the previous system diagram, do not do super resolution on the server, do it only on the client, because the bits you are going to pay are not worth it. You are better off to send, for example, at this bit rate, this point rather than this point. The convex hull is still the good old linear methods. But when it's done on the client, you don't send bits. So you get the improvement without bits. On the server, you pay for the additional bits. But let's go to coffee. This is gonna be a long discussion, okay? Yeah, the top extends. So that's the only thing you should do. Exactly. Only when you extend your quality range. But for the quality range offered by traditional methods, there is no real gain. But anyways, this again a long discussion. Let's go for coffee. Let's try to resume at 3:30. Lucas.
Everybody stays here. I'm going to keep you from coffee. I just want to focus on the other spectrum, not the bottom quality, but the top. And that you really identified really well the drawbacks, for example, the color artifacts and the over sharpening. The problem I see is that in the subjective protocol that you use, there is no check for those. And if you show me the two grapes, which one is worse or better, I don't have a reference. I'm just going to pick one that is potentially sharper. If I'm a crowd worker, I'm just going to spend probably half a second on it and just click the same. If you have a crowded picture, there's going to be just this one looks sharper. I'm going to click on that. Did you observe this in your data? And is this data then to be used to draw conclusions from? Because my worry here is that we're saying, okay, now we are able to trust this metric, or this super resolution algorithm is better than this one, but this is baked in and potentially even in the data. So did you do any analysis, or are you planning to do any sort of data pruning with this regard?
So I'm trying to understand your question. Is the question that a certain type of artifacts not well explained in the protocol can bias the subjective rating results? Is that your question? Yeah, I think that is always a challenge for us doing this evaluation, because at that a certain magnitude, like hundreds of videos, is not practical for engineers to go over all of the videos, and so there will always some kind of artifacts not well documented in the rating guideline. And what we are doing is more like a iterative approach, sharing enough examples for the artifacts we already know, and adding more examples in the future iterations identified in the previous evaluation. So it's not a one-stop, it will be continuous. We will track the quality over a long time to draw a conclusion. So this is more like a version 1 conclusion. So we will have follow-up iterations.
I see a lot of interest, and because we have time, let's break for coffee, come back, and continue questions, okay? Is that a compromise accepted? All right, coffee break, maybe stop the recording.